Problems in Fluids 2, number 7. A barrel of oil is a cylinder that holds 55 U.S. gallons of oil. A drum is nominally 0.880 meters tall, 0.610 meters in diameter, which I've already shown is a radius of 0.305 meters. Suppose it is full of oil with a density of 800 grams per cubic centimeter, 0.800 grams per cubic centimeter, and that would be then multiplying by 1,000, 800 kilograms per cubic meter. Assume that the bung, which is the little screw-in top in the top, the bung is open. Loading into a freighter, a worker inadvertently punches a hole in the bottom of the drum. The hole has a diameter of 0.5 centimeters, which we will make that to be the radius of the hole at the bottom, 0.25 centimeters. Definitely, when you see these problems, get everything converted as soon as you see them to the units that you need. We need radius here, not the diameter. What is the initial velocity here of the oil coming out of the drum? Now, let's go to Bernoulli's equation. We have the pressure at 1, which we're going to call the top part up here, plus rho g, we'll call it y1, which will be this coordinate here, plus 1/2 rho times the velocity at 1 squared, that's the velocity of the oil coming into the drum or flowing down through the drum from the top, is equal to the pressure at 2, that's at this point here at the bottom, plus rho g y2, this will be the y2 elevation, 0.880 meters below y1, plus 1/2 rho v2 squared. Now let's collect this. I have P2 minus P1. I know P2 is a greater pressure, so I like subtracting this way so that I get would normally get a positive number here. So if I put and group these together, I get rho g times y2 minus y1 plus 1/2 rho times v2 squared minus v1 squared. Now we can make some simplifying things that are going to help us a lot. First of all, the bung hole is open at the top and it's coming out at the bottom. So the pressure 1 and the pressure 2 are the same. So this entire term is 0. They're both open to the atmosphere, so those pressures are the same. Second of all, let's choose y1, which is at the top, to be 0. So we'll make our coordinate up here to be the 0 point. Finally, let's look at the velocities down here. The velocity 2, where it comes out, is much, much greater than velocity 1, because velocity 1 is the top up here. So let's look at our assumptions. We have P2 equal P1 because both are at atmospheric pressure. I have Y1 equals 0 because I selected it that way. And I have the velocity at 1 is much, much less than the velocity at 2. So in this part where I subtract them, I can ignore velocity 1 because it's so much less than velocity 2. Why is it so much less? Because I've got a little bitty hole with oil pouring out that hole, and the top of the drum, which is a big barrel, is just going to go down very slowly. Now if I look at what's left of the equation, the differences in pressure is 0. And that leaves me with rho g y1 is 0, so that only leaves me with y2 plus 1/2 rho v1 is so much less than v2, and I'm squaring them, so that's the only terms I have. I can cancel out the rows, and I'm left with 0 equal to g y2 plus 1/2 v2 squared. I want velocity 2, so I solve it for velocity 2, and I get the square root of minus 2 g times y2. So, therefore, it's the square root of minus 2, 9.8 meters per second squared, Remember, if we call this 0, then y2, this measurement here of 0.880 meters, is a negative. Taking the square root of that, I get 4.15 meters per second as the velocity of the fluid flowing out of the oil drum. Note that actually it's independent of the density of the fluid.